Hello students, once again I am here with the continuation of class 10 mathematics chapter 1 exercise 1.2. In the previous video I have done exercise 1.2 up to question number 4. So today I am continuing with question number 5, and question number 5 is check whether 6 power n can end with the digit 0 for any natural number n. The question is this: check whether 6 power n can end with the digit 0 for any value of n. Means 6 power 1, 6 power 2, 6 power 3, 6 power 4 and so on. Is any of this number can end with the digit 0? You must know one basic thing. For any number to end with the digit 0, that number must have 2 and 5 as its prime factors. All the numbers having the prime factors 2 and 5 can only end with the digit 0. So in order to check whether 6 power n will end with the digit 0 or not, we have to find the prime factors of this base number, that is 6, and we know that the factors of 6 are 2 and 3 only. 6 is 2 into 3. So 6 power n will be 2 into 3 power n. If 6 power 1 means 2 into 3, 6 power 2 means 2 into 3 the whole power 2. Only this 2's and 3's will be increasing in number, but it is not going to have 2 and 5 as its factors. Do you follow my point? Since 6 has only 2 prime factors 2 and 3, 6 power n will also have the same 2 factors 2 and 3 only. But a number to end with the digit 0, it must have 2 and 5 as its prime factors. So the answer is no. 6 power n can never end with 0. Can never end with the digit 0. I hope this point is clear to you. So in order to solve this type of question, you have to find the prime factors of the base number. If the prime factor of the base number are 2 and 5, then it can end with the digit 0, otherwise no. Next is question number 6. Question number 6 is explain why 7 into 11 into 13 plus 13. 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. What is the question? Explain why this and this are composite numbers. Means you are given that these two numbers are composite. Now you have to explain why it is composite. What is the basic necessity for a number to become composite? That number must have minimum 2 factors other than 1. You know that 1 and the number itself are the factors of every number. Other than this 1 and the number, if that number has one more factor, then that number is said to be composite number. So we have to explain this number and this number have minimum 3 factors. And if we remove that 1, then we have to show that it has minimum 2 factors other than 1. Or if we can show that these numbers can be expressed as the product of two numbers. product of two numbers other than 1, then they are composite. 7 into 11 into 13 plus 13. It can be written as there is a 13 here and there is a 13 here also. So this 13 is common in both. See, 7 into 11 into 13. Till here it is called one term. Plus 13, this is the second term. Plus or minus sign separates the terms. So here and here 13 is common. What is left out inside? 7 into 11 into 1. If you leave that 1, then plus 13. 13 is gone outside. So it is 1. So it is 13 into 7 into 11, 77. 77 plus 1, 78. So we could express this number as the product of two numbers other than 1. So if a number has two factors other than 1, it is composite. So since this number is expressed in this form, product of two numbers other than 1, it is composite number. Now come to this number. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. Now look here. Here there is a 5. Here also there is a 5. So I am taking that 5 common. Inside the bracket 7 into 6 into 1. I am not writing 1. 4 into 3 into 2 into 1 plus 1. 5 into, find the product of this. (1008) plus 1, that is 5 into 1009. Once again we got this number can be expressed as 5 into 1001. Two factors other than 1. If a number has two factors other than 1, then that number is composite. So you may write one more line here. Since this number has two factors other than 1, it is composite. Same sentence, same statement can be written here also. If any number is having minimum two factors other than 1, then all such numbers are composite numbers. So this is the explanation why these two numbers are composite. Now question number 7. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. So there is a circular path and two people are driving around this circular path and they are taking different times to complete one round around this path. Sonia takes 18 minutes. Sonia takes 18 minutes while Ravi takes 12 minutes to complete one round. Now the question, suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? If both of them start from the same point at the same time, since they are taking different time, so they will not meet again in the next round. But they may meet again after some time. What is that time? Or after how many minutes they both will meet again I hope many of you might have got the answer. This is the concept of LCM. This is called least common multiple. Both of them will meet again at the starting point at the LCM of 18 and 12 minutes. Now, one more question. Will they meet only one time again a day? The answer is no. They will meet several times again in the starting point. When and when? In all the multiples of 18 and 12, they will meet again at the starting point. But the question is, when will they meet again at the very next time? That is called least common multiple. Common multiple and least common multiple. They will meet again at in all the common multiples of 18 and 12. Common multiples of 18 and 12. But they will meet at the starting point for the very next time at the LCM of 18 and 12. So the required answer is LCM of 18 and 12, and you have to write the statement. Therefore, they will meet again after these many minutes at the starting point. So please see more word problems of this type. The practical application of LCM. Word problems can come in the exam. So HCF and LCM, that concept must be clear to you. Then only you will be able to make out the word problems, what concept is to be used in this question. So LCM means for the very first time, where will they meet again? That is called least common multiple. Then in all the multiples of this LCM, they may meet again and again. But for the very next time, where will they meet? Least common multiple. LCM of 18 and 12. You know already how to find the LCM of 18 and 12. Do the prime factorization of 18 and 12 and find the LCM. That's all. Exercise 1.2. So LCM, HCF and prime factorization is over with this question. Now we are going to study a new theorem. There is no particular name for this theorem, and the theorem goes like this. If P is P be any prime number and A is any positive integer, and if let P be any prime number and A is any positive integer, then if P divides A square, then P divides A also. The statement may be a little difficult to understand as the previous statements also, but the meaning is very simple. When you understand, when I expand the meaning of the statement, you will understand it clearly. P is any prime number. Prime numbers are 2, 3, 5, 7, etc. And A is any positive integer. If P divides A square, what do you mean by P divides A square? If P is a factor of A square, P divides A square means P is a factor of A square. 2 divides 10. We say 2 divides 10. What does it mean? 2 is a factor of 10. So here the statement goes like this. If P divides A square, then the same P divides A also. I will explain with an example. 2 divides, say 6 square. 6 square 36. 2 is a factor of 36. Then we can say 2 divides 6 also. If 2 divides A square, then 2 divides A also. We know that 2 is a factor of 36 and 2 is a factor of 6 also. You take any such example, everywhere you can see it. We know that 3 divides 6 square. 6 square 36. That 3 is a factor of 36. Then 3 divides 6 also. 3 is a factor of 6 also. In this way, if you take any example and check, you can see if P is a prime number and A is a positive integer, and if P divides A square, or in other words we can say if P is a factor of A square, then P is a factor of A also. This is the next theorem using which we are going to do the next exercise. This theorem has no particular name, but this is the theorem, and remember we are going to use it in the next exercise. So I am going to do the questions of the next exercise. That is exercise 1.3. Yes. Exercise 1.3, question number 1. Prove that root 5 is irrational. Prove that exercise 1.3, question number 1. Prove that root 5 is irrational. We know that root 5 is irrational. You might have studied in class 9 that root 5 is irrational. But that was not theoretically proved in class 9. Is it? The teacher might have told you root 2, root 3, root 5, root 6 like numbers are irrational. Why they are irrational? No, it was not mathematically proved in class 9. Now we are going to prove it. See, there are different methods of proofs in mathematics. One method that we are going to use here to prove that root 5 is irrational is called contradictory method. What is this contradictory method? We will suppose that the given question means we have to prove here root 5 is irrational. We will suppose that root 5 is rational. We will suppose just opposite to that of the answer that we are expecting. Then we will continue the question, and finally we will reach at such a stage where we will come to know that this condition is not possible at all in mathematics. For example, by considering or by supposing the opposite thing of what we have to prove, suppose you proceed and finally you will reach a state where you will get 2 is equal to 3. And we know that 2 can never be equal to 3. So after reaching in such a stage, we will see that it is LHS and RHS are not equal. Then why they are not equal? Then we will think back and then we will say LHS is not equal to RHS, or it is not possible because our supposition was wrong. Our supposition was wrong. Then we will correct the supposition. This is called contradictory method. We are contradicting the statement in the beginning itself. In order to prove root 5 is irrational, we will begin with, let us suppose that root 5 is rational. So here also I am beginning with, let us suppose that root 5 is rational. If root 5 is rational, we can consider or we can represent any root number, any rational number in the form of P upon Q or A upon B, where A and B are integers and B not equal to 0, but we are adding one more clause to this time, that A and B are coprimes. What do you mean by coprimes? Having no common factor. Whenever we express a rational number in the simplest form, you must remember that numerator and denominator will never have a common factor. 2 upon 4 is not the standard form of a rational number. If it is 2 upon 4, we will make it as 1 upon 2. Is it? So we know that the final answer of any rational number will be expressed in the simplest form. So here also a upon b is the simplest form. So a and b should not have any common factor between them. The two numbers having no common factor between them are called co-primes. So here let root 5 equal to a upon b, where a and b are co-primes. Co-primes means having no common factor. Now cross multiply here. B root 5, that is b root 5 equal to a. Now squaring on both sides. Squaring on both sides, we will get 5b square is equal to a square. 5b square equal to a square. See, squaring on both sides. I am taking this as equation number 1. What does that mean? 5b square equal to a square means 5 is a factor of a square. A square is written as 5b square, means 5 into b square. 5 and b square are the factors of a square. Or we can say 5 divides a square. Is it? 5b square equal to a square means 5 is a factor of a square, or other language 5 divides a square. So I write that is 5 divides a square. Therefore, by the previous theorem that we have studied just now, we have studied that if 5 divides a square, therefore by theorem 5 divides a also. If 5 divides a square, then 5 divides a also. Theorem. 5 divides a means what? 5 is a factor of a. If 5 is a factor of a, then this a must have one more factor. At least one. 1 is the factor of every number. So since 5 is a factor of a, we can write, therefore a can be written as 5 into c. What is c? Where c is any integer. C can be 1. If 5 is a factor of a, along with this 5, there must be at least one more integer. Minimum 1. Or it can be 5 into 2, 5 into 3, 5 into 4, any other integer. So since 5 divides a, we can say a is equal to 5 into c, where c is some other integer. Now we are going to put this value of a is equal to 5c in equation number 1. So putting the value of a in equation number 1. Put the value of a in equation number 1. 5b square equal to a square. A square means 5c the whole square. 5c the whole square is 25c square. And continuing here, that is 5b square is equal to 25c square. 5 and 25 got cancelled. B square equal to 5c square. Again see this step. B square equal to 5c square means 5 divides b square also. 5 is a factor of b square, as we have seen here. 5b square equal to a square means 5 divides a square. Here we got 5c square equal to b square. So 5 divides b square. That is 5 divides b square. Therefore, by theorem, 5 divides b also. Since 5 divides b square, by theorem 5 divides b also. Now look at these two statements. We got 5 divides b Here we got 5 divides A. I repeat, in the beginning we got 5 divides A. Now we got 5 divides B. What does it mean? 5 is the common factor of both A and B. 5 divides A, 5 divides B. Therefore, 5 is the common factor of both A and B. But what is our supposition? A and B are coprimes. Our supposition is that root 5 can be written in the form of A upon B, where A and B are coprimes having no common factor. Now what did we get? 5 is the common factor of both A and B. Are they not contradicting each other? Yes, they are contradicting each other. Our supposition is that A and B are coprimes, but we got 5 is the common factor of both A and B. So it contradicts our supposition. So you will write the next one. We got 5 is the common factor of both A and B. But our supposition is that A and B are coprimes. Therefore, next line. Therefore, our supposition is wrong. Therefore, our supposition is wrong. What was our supposition? A and B are coprime. And from where did we get this A and B are coprime? We have supposed that root 5 is irrational. This is our actual supposition. From there we got this line. So our supposition is wrong. Therefore, root 5 is irrational. Therefore, root 5 is irrational. I hope that the steps are little confusing or little lengthy. No problem. You may go through this video once again or twice, thrice. And there is a systematic way for proving this. So, this is the method which is known as contradictory method. In this way we can prove root 2 is irrational. Everything will be followed as it is. In case of root 2, you will get 2 is the common factor of both A and B. In this way you can prove root 3 is irrational. There we will get 3 is the common factor of both A and B. Question number 2 of this exercise is, no, 2 and 3 are different, very easy. 2 and 3 are very easy. But in the example, in the book you are given root 3 and root 2 also. So, all of you try the same thing for root 2 and root 3 also. So today's homework, prove that root 2 is irrational and prove that root 3 is irrational. So that's all for today. Please go through the questions and its answers, solutions once again carefully and see the video again and again until and unless you understand it completely. Okay, take care. Thank you for watching me. So see you again in the continuation in the next video. Till then, bye bye.